In this paper, we present a lawful algorithm to prepare the correspondence information for the visibility functions. For the all-frequency global elimination rendering, the visibility information is an important attribute to consider. In the previous approach, it was represented in vector forms and pre-computed for each vertex. If we prepare the correspondence of each triangle for this representation, we can interpolate the visibility and therefore allowing a more flexible and efficient manipulation. To prepare the correspondence, we place the third visibility of a triangle to a spherical vonoid diagram, colored in red, green, and blue on the screen. Examining the diagram carefully, we'll find that there will be some spherical vonoid vertices with all three colors in its neighborhood. Since a vonoid vertex is a tripole on its own, its mapping gives us an ideal primitive correspondence information, namely a triple. Then we select from these triples and form a list per triangle. When we select a triple for a triangle, it will influence the adjacent triangles too. To be precise, a selected triple will propagate 3 single-linked triples to its adjacent triangles. This results in the presence of the single-linked triple besides the complete triples. For the single-linked triples, we extend them to become complete triples. During the extension, 2 single-linked triples will be propagated to the adjacent triangles. This results in even more single-linked triple and complete triples. At the end of the selection, the remaining single-linked triple and the empty slots are filled by considering the least totering. Providing the correspondence, we can interpolate the visibility. Showing on the screen is the transition of the interpolated visibility when a sample point is moving along the triangle. This interpolated visibility can be used directly during the perfectment global elimination rendering. This is the perfectment rendering results of a cross object illuminated by 400,000 light sources. It is interesting that the randomly scaled consistent correspondence is already sufficient to render some visually appealing results. Although some things might potentially occur, they are unlikely to be picked up visually. We include a comparison to some Monte Carlo methods for the evaluation. To improve the rendering quality of Monte Carlo methods, we can increase the sample per pixel. However, this will also increase the processing time. This is how the visual quality evolves when the sample per pixel increases. With similar processing time, our method has a higher PSNR, and this quality improvement can also be observed visually. With the denoiser, the rendering quality of Monte Carlo methods can improve dramatically. However, the processing time will be longer due to the overhead. With similar PSNRs, our method has a 4 times as fast rendering speed. Note that PSNRs only reflect visual quality from a macroscopic point of view, and similar PSNRs do not necessarily imply similar visual quality. Here are some more elaborate rendering results rendered with our algorithm.